So today we will continue our discussion on CPU scheduling. Today's lecture is going to focus on real-time scheduling. Okay. So in fact, last time we started talking about real-time scheduling, and we made the distinction between two different concepts: hard real-time systems and soft real-time systems. So what do we mean by hard real-time systems? What kind of systems are these? And what do we mean by hard in this context?
Embedded systems. Embedded systems.
Yeah, and so why are we using the word hard here? What does it mean? Yes.
It's talking about like critical systems, like NASA, for example. You have these systems in an advanced hardware that need to hit these deadlines at certain times. Certain calculations need to be made at certain times, otherwise something could fail.
Yeah, exactly. So hard here means you have a certain deadline, or you have certain deadlines for the processes. And if a process does not complete within that deadline or by that deadline, then the system will fail. So that's why it's a hard deadline. If a deadline is missed, the system will fail. That's what we mean by a hard real-time system. And usually this is the case in embedded systems. Systems that or computers that control machines or devices or any application. But in general purpose computers, with general purpose computers like your laptop or desktop or server, usually we don't have hard deadlines. So all what we need is to have a priority-based scheduling system in which some processes get the highest possible priority. And that's where some general purpose operating systems, including Windows and Linux, support a real-time priority to be just the highest priority in the system. So real-time processes are just the highest priority processes, but we don't have the notion of a deadline. That's a soft real-time system. So soft real-time system simply means supporting real-time priority as the highest priority in the system, but there is no defined deadline for each process. It just means high priority, or the highest possible priority. And we talked about the different delays last time, or latencies, and we said that in a real-time system, these latencies should be minimized. So the latency between the arrival of a process, in an embedded system, the arrival of a process is a task that is responding to an event that is happening, that got detected by a sensor. So the sensor detected something, and then in response to that, there is a process will have to be executed. And we would like to minimize the delay between the time that event occurs and the time it actually gets the CPU. And that delay includes the time that the system needs to handle the interrupt first, because it's interrupt driven. So when an event happens, that generates an interrupt, and the interrupt gives control to the kernel, and then the kernel will have to resolve that. First, it will have to identify the interrupt, what kind of interrupt this is, and call the right interrupt service routine, and then it will have to store the state of the process that lost the CPU. Then it will have to run the scheduler, and the scheduler will give the CPU to the process with the highest priority process, which should be in this case, if a real-time event has happened, that process should get the priority. But there is the context switching and all the processing that the operating system has to do in order to take the CPU from the process that is currently running on the CPU and give the CPU to the high priority process that has just arrived. Okay, so now we will look into scheduling algorithms. Well, first of all, we say that with soft real time, all what we need for soft real time is just a priority-based preemptive scheduler. So you need a priority-based preemptive scheduler. So why preemptive? Because you want it to be, in order to support real time as the highest possible priority, you want that scheduling to be preempted so that you can always preempt the current process, the process that is currently running on the CPU, and give the CPU to the real-time process that has just arrived. So that's why you need preemption. And of course, you will need a priority-based scheduling algorithm so that you can put real-time processes at the highest possible priority level in the system. So that's soft real-time. Now, in hard real-time, with hard real-time, we will look into a special kind of processes, which are periodic processes. So periodic processes are the processes that have CPU bursts arriving on a regular basis with a certain period. So CPU bursts arriving periodically. So here in this case, P is the period, and T is the length of the burst, and CPU bursts keep arriving periodically. So if P equals 100 and T equals 20, this means that every 100 time units, you will get a CPU burst of length 20. So you will have bursts arriving at times 0, 100, 200, and 300, and so forth. And at each of these times, you will get a CPU burst of length 20. Now, clearly, your deadline must be somewhere between T and P, because the deadline for that process must be longer than the length of the CPU burst. But this CPU burst must be executed by the system before the next CPU burst arrives. So we want to execute a CPU burst before the next burst arrives. Okay. So basically, our deadline cannot exceed, our deadline D cannot exceed P. So it must be greater than T, but it cannot exceed P. In fact, in the examples that we will be looking at today, we will be assuming that the deadline D equals P. Deadline D equals P means that if the burst number 1 arrives at time 0, then the system must complete executing CPU burst number 1 before CPU burst number 2 arrives, and that will happen at time 100. So it must be done before time 100. Okay? So this is the this is the nature of the processes that we will be looking at in this in real-time scheduling. Okay, so we will be looking into two different algorithms. The first algorithm is rate monotonic. Rate monotonic scheduling is a scheduling algorithm for real-time processes that basically says processes with shorter periods should get higher priority. So if I have multiple processes in the ready queue, I'm going to give the CPU to the process with the shortest period. So in this simple example, I have two processes. The first process with a period of 50, CPU burst length of 20, and a deadline of 50. The other process has period of 100, burst length of 35, a deadline of 100. So in this case, a rate monotonic scheduling algorithm is going to say, okay, process number one has a shorter period, so I'm going to give it the highest or the higher priority in this case. And this priority is going to be fixed. So the system is not going to change the priorities. It will always give P1 higher priority than P2. Okay, so now let's see how this works. At time 0, we will have, let's first show the different CPU bursts here. So for P1, we will have bursts arriving at times 0, 50, 100, 150, 200, etc. For P2, we will have bursts arriving at 0, 100, 200, 300, etc. So at time 0, we will have the first burst of P1 and the first burst of P2. Now, these two bursts are there at time 0. So the system is going to say, okay, I have P1 and P2. I will give the CPU to the process with the shorter period, which is in this case P1. So P1 gets the CPU. At time 20, this burst will complete because the length of the burst for P1 is 20. So it's going to complete at time 20. At time 20 now, what do we have on the ready queue?
P2.
P2. So P2 will be in the ready queue. And the system is going to give P2 is going to give the CPU to P2. Now, what's the next event that the system will have to respond to? Yeah.
P1 back in the ready queue?
Yeah. P1 back in the ready queue. Why?
Because the period will end before P2 completes. Or the period will restart before P2 completes?
Well, it's not that the period will start. Well, each process will have its own period, right? So P2 doesn't care about the period of P1. So it doesn't mean anything to P2 itself. Yes?
Does it mean a time quantum?
Well, no, it's not a time quantum here. So there is an event here, which is the arrival of the second CPU burst of P1. So the event that will take place at time 50 is the arrival of the second burst of P1. So these bursts keep arriving periodically, and whenever a new burst arrives, the system will have to respond to that and will make the scheduling accordingly. So this second burst of P1 arrives, so the system is going to say, okay, now on the ready queue I have both P1 and P2. Now the system will have to decide whether to keep the CPU with P2 or give it to P1. So whether to keep it with P2 or preempt P2 and give the CPU to P1. And this decision here, in this case, will be made based on what? Based on?
Auto period?
Period. Yeah, based on the period. And the period of P1 is 50, period of P2 is 100, so P1 will win. The process with the shorter period is going to win. So P1 wins, which means it will win the CPU, which means that the system is going to preempt P2. So P2 will get preempted, the CPU will be given to P1, and the length of the CPU burst of P1 is 20, so at time 70 P1 will be done. At time 70, the system will look at the ready queue, How many processes do we have in the ready queue at time 70? Only one process, which is P2, because P2 got interrupted here. How much time does P2 need? How much time does P2 need?
Just 5.
5. Why? Because it took 50 minus 20, that's 30. So P2 took 30 out of 35. So P2 already got 30 here. And the total that it needs is 35. So it needs 5 more. Okay? So it will get 5 more and it will finish at 75. Now when the burst of P2 finishes at 75, did any process here miss its deadline? No process missed its deadline. So we are fine. So we're meeting the requirements of the system. So both processes were scheduled within their deadlines. P1 completed at 70. The second burst of P1 completed at 70. With the deadline of P1 being what? Of this burst of P1. What's the deadline of this burst of P1?
It's 100.
What's the deadline of this burst of P1?
100.
100, yeah. But the deadline for the first burst is 50. The deadline for this burst is 100. The deadline for the first CPU burst of P2 is 100 also, and it's completed by 75. So each one of them completed by its deadline. And in fact, at time 100, everything will repeat. So we'll have a new burst of P1 and a new burst of P2. So here, the scheduling algorithm was successful at scheduling these processes and meeting the deadlines, and we have no problem. Now, to make it harder to schedule, how do we make it harder to schedule here? How do we make this scheduling problem harder? If I ask you to change these numbers to make the problem harder, what would you do?
Increase the T.
Increase the?
T.
Yeah, exactly. Increasing T, increasing the lengths of the CPU bursts, that's going to make it tighter. And what else will make it tighter? Shorter periods. Yeah. If you shorten the periods or lengthen the CPU bursts, that's going to make it tighter and harder to schedule. Of course, sometimes it's so tight that it's impossible to schedule without missing deadlines. Right? So for example, if we keep the lengths of the CPU bursts at 20 and 35, and we make the period of P2 50, this will be impossible to schedule without meeting the deadlines, right? So if we make this 50, this means that both of them must complete by time 50, but the sum of their CPU lengths is 20 plus 35, which is 55, so it's impossible to do 55 within 50 time units. So it's not always possible. But now we're going to make it tighter, but still possible to schedule. It's still doable.
Question.
So we're going to lengthen the CPU burst of P1 from 20 to 25, and we're going to shorten the period of P2 to 80. So now we have a tighter scheduling problem, and we will see whether this algorithm is going to succeed or fail. Okay, so it's going to do the same thing. At time 0, it's going to say, okay, I have P1 and P2, and P1 has a shorter period. I'm going to give the CPU to P1. Time 25, P1 completes, P2 gets the CPU. Now the decision will have to be made at what time? Time 50. The system will have to make a decision with every new arrival. When there is a new arrival, or when there is a process, or when there is a CPU burst that completes. So with the new arrival, the system will have to decide whether to give the CPU to P1 or P2, but with these periods, P1 has a shorter period, so P1 gets the CPU. P1 gets the CPU, so it's going to preempt P2. P1 has a CPU burst of 25, so 50 plus 25 is 75. At time 75, P2 gets the CPU. Now, how much time does P2 need?
15 more.
Yeah, it needs, no, 10 more, because it got 50 minus 25, that's 25. So it got 50 minus 25, that's 25, and the total is 35, so it needs 10 more. It needs 10 more, and we gave it the CPU at 75, and its deadline is 80. So can it meet its deadline?
No.
It will miss its deadline. So here, P2 will miss its deadline. So the scheduling algorithm in this case has failed. Okay. So now we will look into another algorithm that will do a better job in this case. But let's see if we can figure out how to fix this, or what the better algorithm will do in this case. You know? Where is the problem? Can you identify here the bad decision that this scheduling algorithm has made? Where's the bad decision that this algorithm has made? Can you point at that bad decision? Put your finger on the bad decision.
P1 PM P2.
P1 preempting P2?
Yeah.
So that was a bad decision. Yes. Now, can you think of a criterion based on which we will here keep the CPU with P2? So the criterion that the next algorithm will be looking at. Yes?
What are deadlines closer?
Yeah, exactly. So the next algorithm is going to look at the deadlines. So it's not going to look at the period. You know, the period is a fixed thing, but the deadline is a dynamic thing. So it's the next algorithm, which is called earliest deadline first, it's going to look at the deadline, calculate the deadline at each, whenever it needs to make a decision. It will calculate the deadlines and will give the CPU to the process with the soonest or closest deadline. Okay, so earliest deadline first, we are going to apply it to the same instance, with the same example, and we will be calculating, we will be tracing the algorithm by calculating the deadlines at those time points where a decision must be made. So first decision is at time 0. At time 0, I have, the first CPU burst of each one of them, and the deadline of P1 is what? What's the deadline of P1? Deadline of P1 is 50. Deadline of P2 is 80. Deadline of P1 is 50. Deadline of P2 is 80. And 50 gets the CPU. So the system is going to give the CPU to P1. Well, the next decision will not have to be made until time 50. At time 50, because there is a new arrival, at time 50, second burst of P1 arrives. With the second burst of P1 arriving, we have the deadline of P1 equals what? What's the deadline of P1 now? It's the deadline of the second burst. So that's what? 100. Because it's the second burst. And the deadline of P2 is 80. Still 80 because we're still in the first burst. Okay. And with these deadlines, P2 wins. So P2 in this case will not get preempted. P2 is gonna keep the CPU. At time 60, P2 will be done, Now, at time 60, the system will have to make a decision, but it has no choice. It has only one process in the ready queue, which is P1. So it's going to give the CPU to P1. So that's an easy decision. There is only one choice. So it's going to give the CPU to P1. Then at time 80, the system will have to make a decision again. At time 80, we have the second burst of P2. All right. Then the deadline of P1 is still second burst, so it's what? 100. Deadline of P2 is 160. Why? Because it's the second burst now. So this is second burst, and this is second burst as well. And of course, P1 wins. So at time 100, at time 80, a new burst of P2 arrives, but its deadline is still 160, while the P1 burst that is on the CPU has a deadline of 100, which is much sooner, so P1 gets the CPU, and P2 does not preempt P1. Then at time 85, the system will have to make a decision, but again, this is an easy choice because there is only one ready process, which is P2. And at time 100, there is another decision to be made. At time 100, what do we have? What's the event at time 100?
P1's deadline.
The arrival of which burst of P1?
Third.
Third. So it's gonna, at time, we have third burst of P1 arrives. And now the deadline of P1, because it's the third burst, what's the deadline? 150, because it's third burst. And deadline of P2 is
160.
160, which is the second burst. And P1 will win again. So at time 100, P1 will win. So now with P1 winning, it's going to preempt P2. So P2 will get preempted, and P1 will get the CPU. It will get the CPU for 25 time units. Then at time 125, P2 gets the CPU. How much time does P2 need? It needs 35 minus 10, minus 15. So this is 15. 35 minus 15, that's 20. So it's going to take 20 time units from 125 to 145. And here, all processes will meet their deadlines. Okay. So, any questions on this algorithm, on earliest deadline first scheduling algorithm? So it's very intuitive. We're trying to meet the deadlines, so we just give the CPU to the process with the earliest deadline. So it's a quite intuitive algorithm. Yes?
So both processes have the same time differential between deadlines. How is that resolved?
What do you mean the same? Oh, if there is a tie?
Yeah.
Yeah, so if there is a tie, you will need a tie breaking scheme. You can look at the period, you can look at other things, or break the ties arbitrarily. So whenever there is a tie in any scheduling or in any algorithm, you need a tie breaking scheme. One possible tie breaker is the period. So you can look at the period. Give it the shorter period, or other criteria like arrival time, maybe. Yeah.
in most cases, are the period and deadlines set by the OS, or is that going to be set by the process itself? And like,
Yeah, by the processes, by the nature of the process. So the process, each process declares its deadline to the system.
got it.
Yeah, so each process has a deadline that is that depends on the nature of that process and what it does and how long it needs the CPU for. And the system will schedule the processes based on their declared deadlines. Okay. Any further questions on this? Yes.
It can be noticed that the deadline, the period of these two processes, it has been till like from 140 to 150, whereas in the previous algorithm that we did, it was about 85. So how does that affect, which one do we prefer at times?
What do you mean the 85? Oh, we only looked at 85?
That's right.
Well, it's here we didn't continue because we just failed. Because of the failure, because the process missed its deadline, so we just declared failure and we didn't continue
Okay.
with the scheduling because of the failure. But here, because we succeeded, so we continued on. In fact, when the next bursts arrive, it's going to be we will not have a problem. So this will continue. We will maintain correct execution by meeting all the deadlines.
So if a process sets its deadline, but then more processes keep coming into the queue, obviously it will quickly become impossible to meet deadlines. Is failure just an option, or do we have to like reset deadlines or modify them based on how many
so
processes?
it's a system design thing. I mean, if we're talking about periodic processes, if the design of the system cannot be designed with deadlines that are impossible to meet.
Okay.
So the designer of the system is responsible for designing the system such that the deadlines are meetable, that you can meet the deadlines. So that's the system design issues, but definitely not all deadlines can be met. And we gave an example of deadlines that cannot be met. Okay. So now we will look into the POSIX APIs and how we will look into one API that is related to soft real-time scheduling. Last time we talked about the attribute structure that is used in the POSIX APIs. The attributes, which is a structure that has certain attributes for each thread. And who remembers the attribute that we looked at last time? So there was an attribute, a scheduling related attribute that we looked at last time.
Priority number?
What's that?
I think it was a priority number.
No, it was not a priority number. It was the contention scope. The contention scope. So we had the process contention scope and the system contention scope. What does each one of these mean? Who remembers what these mean? Process contention scope versus system contention scope. Yeah.
I think process contention scope has to do with competition within the process.
Yeah.
While system has to do with a system-wide competition.
Yeah, exactly. Exactly. So that was one scheduling attribute. Today we will look into another scheduling attribute, which is the scheduling algorithm for real-time processing, for real-time scheduling. So the system allows you to set the scheduling algorithm to first in, first out, or round robin for real-time processes, the highest level of priority in the system. And there are set and get methods. So there is a get scheduling policy that extracts the policy from the attribute structure. And here's an example. So we have this attribute, we initialize it with the default attributes. Then we use the get sched policy to extract the policy for real-time scheduling from that, and we can print it. So it could be round robin or first in, first out. And we can, there is also an API for setting that. So we can set that to first in, first out or round robin.